Hello YouTube. In this video, I'm going to be diving into how do we create paths, rivers and splines that traverse and conform to our terrain for large open worlds inside of Unreal using Houdini engine. When I started my journey into Houdini, I was inspired by this set of videos, which came out all at about the same time, which explored the problem of how do we build big open worlds using Houdini. And one thing that they all touch on is the creation of paths and splines, which adapt to the terrain, avoid obstacles, and create interesting patterns as they traverse across it. I want to give a quick shout out to Owen Himes, who was one of the people who inspired me when I first started my journey into Houdini. And I just want to shout out as well his Massive Worlds Toolkit, which he'll be presenting at this year's Everything Procedural conference. So if you want a ready-to-go solution that handles all of these kind of workflows relating to how do you build massive worlds inside of Unreal using Houdini engine, and you want something that just works out of the box, this is a great place to start. If you didn't already know about it, the Everything Procedural conference takes place every year in Breda. It's an amazing place to come and grow inspired and also to network and make friends. I'll be there along with the rest of the Project Pegasus team, and we'll be talking more about our work on Project Pegasus and how we've expanded on and continued the work that we did last year. We're going to be taking a look at the Find Shortest Path node, which is the backbone of all of these approaches. And we're going to take a look at how we can use this inside of Houdini and really push it to its limits and master it, and learn how this tool can be used to create intricate and beautiful patterns on our terrain. I did explore this topic briefly in last year's Project Pegasus, and there are two parts of this tutorial series which look at procedural trails and custom paths, but I never really developed the workflow to the full extent that I'd hoped to, and this is what this and subsequent videos that I'll be producing hope to address. So let's jump inside of Houdini. To begin with, let's just start with a simple example using the Find Shortest Path node. As always, once we open Houdini, I'm going to jump inside of a geometry container. I'm just going to throw down a simple grid in the Find Shortest Path node. The clue's in the name, but for those of you who don't know, the Find Shortest Path node is able to find the shortest path between a set of points. We can see here that it's finding the distance or the shortest path between point 0 and point 15 on this grid, so 0 being here and 15 being here. And I just want to show these both together. So I'm going to switch the display over. I'm going to make sure grid is disabled so I can see the geometry. And I'm just going to go to the visualization tools settings, and I'm going to change Y width so we can see clearly what happens now if I change the target point. It's finding its way across the terrain. We can already see that in principle it's working. It's finding the most direct route using the edges of the geometry. It's not tracing some bizarre path all around. One thing you may be picking up on already is that we can see this kind of zigzagging pattern. And if we saw this in the end result inside of our game engine, it would look very unnatural to say the least. So instead of generating a regular grid in the way we're doing here, I'm going to scatter some points on the grid. And I'm going to set the density to be quite high. And then I'm going to fuse by a set distance. Let's say 3 will do here. And what that gives us is relatively evenly spaced points across that grid, which are not arranged in an irregular fashion. And if I go to a smaller fuse distance, we can see that they're spaced even more closely together. Now I can use the Triangulate 2D tool here to produce a new kind of triangle grid. It's not really a grid anymore, but this new set of triangles, this triangular geometry. And we can do the same exact thing here. And we can see that straight away now, it's just searching, looking for the shortest route between point 0 and 65. So actually, let's have a look and pick 2 points that are further away from each other. I'm going to go from 77 to 568. And now we can see that we're getting a much more natural looking path. So what do we learn from this example? We learned that the quality of the end result of the Find Shortest Path node is highly dependent on the source mesh that is fed into it. We're going to be thinking about this, and we're going to be holding this idea in our head as we proceed onto progressively more complex examples. Of course, traversing a flat plane is never going to yield very interesting results. So let's begin by creating a slightly more interesting height field to play with. I'm going to begin by throwing down a standard height field node. I'm just going to hide the old Triangulate 2D there. And I'm going to throw down a curve node as well here. What I'm looking to create is an island, which is somewhat reminiscent of the island that we created on Project Pegasus. I'm going to switch to the orthographic view by pressing 2 on the keyboard and select the curve node. And then by hitting enter on the keyboard, we've entered the curve tool, and we have the ability to place down spline points. And what I'm going to draw out is a set of curves that are going to define a mountain range. What I'm doing when I finish a portion of the curve, I'm just hitting enter, and then I can left click and start drawing again from somewhere else, like so. And we'll have a look at what this looks like. For now, I think that will do. I'm going to put down a quick little volume wrangle. I'm going to plug the height field into the left input. I'm going to plug the curve into the right input. And I'm just going to call this curve ridge lines. Now, inside of the volume wrangle, I'm going to say at height equals x, y, z dist. And then we're going to look at the first input, that is the second input, but it's index 1 of the volume wrangle. And we're going to be looking for the distance from the current point to the nearest point on the look what we get. Okay, interesting, but arguably upside down. I'm going to put down a quick little height field remap, like so. And I'm just going to hit compute range so we can see the min and max height. And then if I just flip the curve, we're starting to get something a little bit interesting. If I just enlarge the curve preview here, what I can do now is I can start to set the edge of the island. Not bad, maybe a little bit further. And then I can pull down the maximum height I want and start to kind of play with the profile of the island here. I think 200 meters is still kind of pushing it a little bit. And right now it feels like we're starting to get somewhere, but it's maybe a little bit too. I'm going to go and add a little bit of noise to the position of the curves. And let's have a little look. Okay, we're starting to get something a little bit more varied. Remember, we're just trying to set up a quick little prototype and we're not being too fussy. We'll call that done for now, but it still looks a little bit too synthetic. I'll add some noise. Okay, we'll go with that. And then I'm just going to do a very quick little flow field on top of the terrain there. And then I'm going to use Heightfield slump to kind of level that out a little bit. So I think I'm starting to feel all right about this. I'll just increase the resolution this to 2. And I'll do another Heightfield. Okay, and maybe what I'll do as well is put a quick little Heightfield distort by noise before the flow. Okay, so that introduces a little bit more breakup. The Heightfield flow, make sure that I'm adjusting the height once more. And finally, I'll do a Heightfield mask by feature and one more Heightfield slump. And I think that this is going to do me for now. So what I'll do is a Heightfield mask clear. And this is the island that we're going to be working with for the course of this tutorial. As mentioned previously, and as shown in the previous example, the find shortest path node relies on a mesh. So the first thing that we're going to want to do is we're going to want to convert our height field into a mesh grid. We could use the height field node, which is a default Houdini node that will do what it says on the tin. Turn off the point number display. We can see that we get geometry from our height field, so we're no longer dealing with volume. However, if we look closely, we'll see that we have a regular grid. And again, as shown in the previous example, a regular grid is far from ideal when we're talking about how points can move across a surface, because we'll see this kind of stepping. We'll do what we did previously, but on a larger scale. We'll use a scatter followed by a fuse and then a triangulate 2D. But before we do this little process here, I'm just going to put down a null node to stay organized. Now we're going to remove the convert height field, and we could use a scatter node or a height field scatter node to create the points. But to speed things up a little bit, what we're going to do instead is we're going to use points from volume, which allows us to set grid resolution, points we want to spawn, as well as set a jitter scale, which allows us to add some irregularity. We can see that if we zoom out, we're not getting every portion of the height field. And that's because there are some portions of the height field which are below 0. A simple fix for this: compress the landscape down slightly so it's less tall. There's a slight difference, but not enough for me to be bothered about it. Now we can see that we have an irregular grid of points. And using the same technique before, I'm going to use a fuse where I set the resolution, the triangle mesh, and that gives us a separation of 2 meters between every single point. At least we have a nice irregular set of points, and I can use triangulate 2D, which after a little bit of thinking is going to produce a dense triangle mesh that's irregular and perfect for pathfinding. But currently it's completely flat, as we can see. So what I'm going to do for the triangulate 2D, or it can be after it actually, doesn't really matter, is I'm going to take every point and do a ray cast towards the height field in the direction of 0, 1, 0, that is up, and transform the points to the desired position. This blue color indicates that the geometry is currently reversed, and I want the top to be considered the front face and the bottom the back face. So I'm going to go to the triangulate 2D, where it says fit positions 2D projection plane. I'm just going to set this to manual before I do anything, make any changes. I'm going to select the projection plane, and we can see that it's actually already set to the correct direction, with Y being the upper. If I switch back on mouse update, we now have our irregular triangular representation of the terrain at a resolution of roughly 2 meters per point, which should be more than enough for our pathfinding purposes. Now we can put down the find shortest path node, and we need to plug in our surface geometry, that is this triangular mesh, on the left side. And on the right side, we have the option to plug in alternate start and endpoint locations. What this means is that instead of identifying 2 numbered points in the original geometry, we can just provide 2 arbitrary points which sit somewhere on that mesh, which will be our start and end destinations. We can do a simple scatter of 2 points on that geometry. Let's have a little look what we end up with. Okay, I'll just change the seed to end up with 2 points that are slightly further away. There we go. For now, that's good. And I will plug those into the find shortest path. Now, we get a little warning when we plug that in. And where's that? Well, it says because no start points are specified. We can also see that no end points. Let's just remedy that and set the start point to 0 and the end point to 1. 0 being the 0th point of the scatter and 1 being the second point, the first point. And now we can see we get pretty much a straight line across the geometry of the terrain between those 2 points. One thing that I'll address straight away is that I imagine this island sitting somewhere in the sea. And the more points that we have to consider for pathfinding, the longer it's going to take the pathfinding operation to complete. I'm going to put down a blast node after the ray, and I'm going to say at p.y is less than, let's try 50. I'm going to make sure that it's looking at points, and that's just going to trim off everything below a certain point. I actually don't like the way that the border of this mesh looks, so instead of that, I'm going to use another node called clip, and I'll set this to be 25, and that's a little bit better. We have our island, and now if we plug that into the find shortest path node, make sure that our scatter is only picking points on that terrain, we end up with something really nice. So I'm going to delete the scatter, and we're going to throw down another curve node, and we're going to switch once again to an orthographic view. What's going on here? There we smooth shaded version of the terrain. I'm going to select the curve, press enter to enter the pathfinding mode, and I'm going to draw a path from this little corner down here, which is going to first target the top of this mountain, then this mountain, and then finally this mountain over here. We have our paths, and I'm just going to wire that in now to the find shortest path node. And we can see that straight away we are getting some paths that are being found between the sort of the beginning portion and the second portion of that curve. But I want to follow the curve in its entirety. What I can do is I can make sure that the output paths node is set from each start to corresponding end, which allows me to plug in a string, like so, of numbers, where 0 is going to go to 1, 1 is going to go to 2, and 2 is going to go to 3, and so on, which now gives us the shortest path between those two, between all of those guide curves. And I'll throw down a quick merge so we can see the result that we end up with, which sticks nice and closely to our input curves, but traverses across the terrain. So this is pathfinding at its most basic, but we want to be able to tell the pathfinding to consider various costs as it traverses the terrain. For example, we want to assign a cost to steep slopes so that the pathfinding tries to avoid them. This is an example that is quite easy to. We'll have a look at how we can do that straight away. If we click on the find shortest path node, we can see that it's outputting already a cost. It already has some cost for traversing the terrain. If we go to the path costs panel, we can see we have a bunch of parameters relating to what are the costs of the points that are being traversed. If we if we tick omit distance from costs, we can see that now, because there are no costs whatsoever, The pathfinding algorithm has no information indicating whether the path it's taken is shorter or longer. And while kind of interesting, a result, this isn't what we're looking for. We'll leave that on for the time being. The thing that we're especially interested in is this point cost attribute. This point cost attribute parameter allows us to specify an attribute on the surface geometry, that is on the triangle mesh that's being traversed, which tells us the cost of traveling to that point. We'll put down an attribute wrangle after the clip for the shortest path. And on this attribute wrangle, we're going to say at cost, and we need to calculate something here that relates to the angle of the. Quick way to do this is to get the dot product of the normal and an up vector. First, we need to construct an up vector like so. And if we want to visualize that quickly, we can set color to be equal to cost. And we can see that some shading has appeared on our terrain there. Now, that's quite subtle. So what we can do is we can use a power operation to increase the contrast. And I'm going to set the power to a value of, say, 6. And what this means is that the white areas have a high cost and the black areas have a very low cost, which is the exact inverse of what I'm looking for. So I'm going to do a 1 minus, and now we can see that the sloped areas are being represented as by white, which means more expensive. I can tweak the power to sort of control the relative value or the relative cost of traversing these different areas. Now, if I just comment out the color, because we're not particularly interested in that, and look at the output of the merge, can we see any results? No, because I forgot to plug in the cost to that. Plug in the cost attribute as the attribute to be read. And we see a slight change, but it's very subtle. And the reason for this is because such a great distance is being traversed that the relative slope cost isn't having much of an impact on the end result of what is the shortest path. So finally, we should add a multiplying factor on that cost to cause it to be valued more relative to the distance that's being traversed. And I need to be very careful about my the order of my operations here to ensure that we're multiplying it up after the 1 minus and not before it. So what we can see is that if we set this to 0, we end up with our initial result that we had previously. Whereas if we set it to 15, it's going to try to avoid taking the steepest routes up the slope. If I go to 25, it'll try even harder. If I go to 55, 1. Now, plugging in these values hard-coded into Vex is never a good idea. So I'm going to change some of these out. For a slope cost parameter, I'm going to hit this little button here, which now gives me this control, which is very easy, where I can assign the cost of going up slopes. Now we have a basic tool that allows us to draw some paths across the terrain. And if I go back to the original curve and middle mouse click and drag that curve point or any of the curve points, we're going to see that the pathfinder is going to try and find the most sensible route between those 2 points. If you've followed along this far, then you may have noticed an issue where as you add more points to the input curve, we don't see that reflected in the output pathing spline across the terrain. And the reason for this is up to this point, we've just hard-coded the source points and target points into these 2 lists on the find shortest path node. So in order to see those new points that get added, we would have to manually type them in, like as you can see. But this isn't a very procedural way to approach the problem, and it'd be much better if these 2 lists could be updated automatically. So what we're going to do is we're going to create a quick little primitive wrangle here, which is going to take the point numbers and create 2 lists, like the 2 lists that we see here. The first list is going to count up from 0 to the second to last number of the second to last point, and the second list is going to count up from the second point up till the last point. So I'm going to create an array called int points. We're going to make that equal to prim points. We're going to get the first index, first input, we're going to get the current primitive number. And actually this is going to be, we'll call this points A, call this one points. We have our 2 arrays, but right now they're the same. Next up, we're going to remove an index from each of these arrays. For points A, we want to remove the last index, points A. Then points B, we want to remove first. -1 is the last index, 0 is the first index, 1 is the second index, and so on. This should be working, but I'm going to remember, I want to encode this into a string attribute. So let's do that now. I'm going to say s at A is equal to sprintf, and we're going to format the string, convert points A into a string there. We'll do the same points B. Sprintf converts anything into a string, pretty much all of the other data types. It's a bit like printing. except to a string attribute. And we can now see that we've got those two arrays, 0 up to 8 and 1 to 9. So we've got the correct ordering of our points, but we want to get rid of all of these other symbols from those two strings. So what I'm going to do is I'm just going to create two variables, string A and string B, same name as our attributes, equals and equals. Copy this up here, or cut it rather, and then we're going to say A equals replace, and we want to replace inside of A every occurrence of a comma with nothing, and we want to do the same for open braces and close braces, and then we want to do the same for B. And I'm sure you programming wizards have a cleaner way to achieve the same result, but hey, I'm just an artist. So now we can see that we've got our A array and our B array, and truthfully, because we only have one incoming primitive, we might as well set this to be a detail wrangle, and then set the primitive number to be 0, because we only have one primitive anyway coming in from the curve. We've got our two lists there. So we can see that our pathfinding algorithm is going to find the path between 0 and 1, 1 and 2, 2 and 3, and so on. And with those two detail attributes called A and B, on the find shortest path, we know that they're coming from the first input. We can use a quick little bit of a quick little expression here. Detail, first input, attribute name at A, index 0. And in fact, because it's a string, we need to use details S, detail with an S on the end, so detail string. So first index, attribute A, like so, first index, attribute B. And if we middle mouse and click on both of these now, we can see that that's retrieving the correct values from the attributes, and this list of points is going to get updated automatically, which means we go back to our curve, we can now delete points and add points with impunity. So we have our first basic pathfinding system, which allows us to sort of create waypoints and have paths which sort of wind their way across the landscape, somewhat responding to the environment. But something's a bit wrong. And I'm going to put the slope cost way, way, way up high to really exaggerate the effect that we're seeing. And I'm going to modify the curve as well. In fact, we'll just disconnect this one and we'll create an entirely new. I can demonstrate the issue that I'm seeing. The issue I'm seeing is that we want to find the pathing between this point at the bottom of the hill and this point at the top of the hill. Well, first of all, I'm not sure that I did the best job there of actually overlaying these in the correct position. So let's have a quick look. I would say I did. Well, first of all, I think we need to ray the input curve points up to the actual geometry. There we go. So that the pathing is more or less where we want it to go to. And the second issue, the one that I actually wanted to draw your attention to, is the fact that even though we have a cost associated with the slope, at certain points, the path is still going to need to go up a steep hill. And the rules we've currently established tell the pathfinding system nothing about how it should move up the slope. And as I'm sure you're aware, in the real world, we don't get these kinds of paths that humans have created, or animals. We don't tend to get the kinds of paths that just go in a straight line. We tend to see a kind of weaving motion. And that's because by doing that sort of weaving up the slope, we're actually avoiding doing too much work. We're able to ascend at a shallower angle. Now, if you remember, if I turn back on this visualization of the costing, we have a cost of being on the slope, and the pathfinding system is going to avoid being on the slope, which is useful in its own right. But we actually want to establish that traveling across the slope is relatively cheaper than traveling directly up it. And in order to do this, we need to establish not just a per point cost, but we need to establish a per edge cost. And not only that, we want to establish a difference between traveling between edges in different directions, because we may want to have a different cost traveling down the slope than we do traveling up it. So for every point, we need to store the cost of traveling to every other point from that point. Put this pathfinding back to how it was before, turn off the visualization. And if we go and have a look at the find shortest path node, we could go and have a look at the documentation, and I encourage you to do so. And what you'll find out from looking at that, what it tells us, is that it's possible to store the neighboring points for each point in an array called neighbors. And then the cost attribute here, if it is of the type array, if we have an array attribute of costs, then the index of the array of costs will be tied to specific point neighbors. Okay, bit of a mouthful, but in practice, it's actually quite simple. For every point, and this wrangle is already iterating over points, let's name this accumulate costs, and let's name this create strings. So for each point that we're iterating over, we want to get the neighbors. Fortunately, in Vex, there's already a function that does that for us. So we're going to get the first index, that's the geometry that's incoming, and we want to get the neighbors of the current. That's at point num. Now, much like before, we're going to say int points of type array. Type int in an array. An array of points which are of type int, which we've now established. So that's already there. We can save that out to an array called neighbors. Format that as an array by putting that ahead of the @ symbol. It's points. We look at the spreadsheet once more, look at the points. We can see that we now have an array of neighbors for every point, which is 1, 2, 3, 4, 5, 6 points long. So we can see that every point here has 6 neighbors, I think. And then our cost here, we actually just need to make sure that that is being encoded as an array. I'm going to move the attribute setting down to the bottom of the wrangle because it's generally a smart practice, and that way you avoid getting it kind of mixed in with your calculations and any loops you might be doing. And we're going to say for each int point in the array points, okay, we are now going to add something to an array of float, because we want it to be a float array, float costs, which by default has nothing in it. Then inside of the array, we can say costs or append costs. That means we're going to add something. And the cost that we want to add is going to be, in this case, what we calculated down here. So I'm going to bring this up here. And for the time being, we can just call this a flat slope cost, float slope cost equals. That's like avoid slopes would be another way of thinking of that one. And we're just going to append slope cost to the costs array. Okay. Now we need to make sure that this attribute cost is also an array of type float, and we're going to set it to be equal to the costs variable. Setting attributes, calculating per point costs, or calculating neighbor costs, or even better, directional costs might be a way of thinking about that. And this one's going to be calculating basic costs, that being just the cost of being somewhere. So maybe a wet region is just generally more expensive to navigate through. And that'll do now. We'll get rid of it because that's not going to help us anymore. And what we should see right now is we haven't actually done the behavior that will change the cost of moving different directions, but we should see we have the same exact behavior as before, except this time the difference is that we're using array. We can see that indeed find shortest path will correctly understand those attributes if there are arrays that are being passed through per point. If we go and look at the geometry spreadsheet, we should see that we now have a cost array, and what we should see is that for every direction the cost is currently the same. So this array here that we're looking at is a single point, and we can see that at this point on the landscape, moving in any direction has the same cost, and that's not what we want. The next thing we're going to do is we're going to initialize a variable called float ascend cost. We'll also do float. In fact, let's just do float ascend cost. We'll say float ascend cost, this is the cost of moving up the hill, is equal to the slope cost. Okay. However, we want to nullify it. We want to nullify this if, in fact, no, we don't want that to be quite right. No. Forgive me. What we actually want to do here now is we want to get the direction of the wire. We want to get the direction from this point to that point. So let's keep that initialized and we'll set the ascend cost to 0 by default. And then we're going to go inside of the loop. And inside of the loop, what we need to do is, well, we're going to say vector current pos equals v at p, okay? And then we also want to initialize target pos, okay? Which is just going to exist. And we're going to set what that is inside the loop. Inside of the loop, we're going to say target precision equals, now we're going to get a point attribute. We're going to get the attribute from the first index, first input to the node. We're going to get p, that's the position. I'm going to get that point that we're referencing here is one of the neighbors, which is coming from the for each loop. So it's the current point that's being iterated on, and we're getting the position. Now that we have the current position and the target position, we want to be able to get the direction between them, and from there we can calculate the cost of the slope, or the amount of slope that there is. We'll be doing that in the same manner that we did up here by doing a dot product between the direction and the up vector. To get the direction between the 2 points, what we can do is we can say float. Let's actually save this out as vector. We're creating a variable called direction, initializing it. Then we're going to say direction is equal to target point minus current pos. I meant to do target pos there. Target pos minus current pos. Okay, that gives us a direction and a magnitude. We don't want the magnitude, we just want the normal, a normalized vector, the unit. We can say vector n for normalized, we're initializing it, and then n equals normalize direction. This gives us the normalized direction from the point to each of the other points. And then finally, we're going to copy this kind of logic that we've got up here, where we're going to say we want the dot product between n and the up vector. And then we're probably going to want to have a power operation once more. So power, and I'm going to stick to 3 because that seemed to work quite well. And then we're going to say ascend cost equals that. Ascend cost equals this calculation. And then we're going to times that by a parameter that we're going to create called ascent, or ascend cost. Okay, I hope you're sticking with me. And now we've created an ascend cost, and it functions very similar to our slope cost, except it's in each direction. So what we want to do now is, to this costs array, we don't want to just add the slope cost, we want to add also the ascend. Okay, so slope cost plus ascend cost equals the total cost of traveling somewhere. Now, we increase the ascension cost, what we should start to see is a windier path starting to emerge. At first, the behavior might seem to be a little bit unpredictable, and indeed it is. And if we just tweak the power value here, we're going to see something interesting. Every time we increase the power, as it becomes an odd number, we end up with pathing that doesn't really adhere to the rule sets that we want it to. But every time we're on an odd number, we get a path that appears, an even number, sorry, we get a path that does actually indeed climb up the slope in a sort of zigzag. Why is this? Well, the reason we're seeing this behavior is because when we do the dot product of the normal or the direction with the up vector, we're getting a negative value when the path is sort of heading down slope. And when you have a negative value and you apply an even power operation to it, it becomes a positive value. But when you have an odd value, a negative number multiplied by itself and by itself and by itself again, is going to return to being a negative value, which means we have a negative cost, which means it's actually seeking out the slopes to walk down them. Now, this is an interesting effect, but it's not the one we're looking for right now. So we're just going to make sure that we do an absolute operation, okay, in between the power, just before the power gets applied. And then we're going to see that as we increase the power, that just has the effect of modifying the kind of character of the slope without sending it off on sort of weird, squirrely paths where it's looking out that it can walk, where it's looking down that it can walk down them. Okay, and this is looking pretty good. And by playing with the slope cost and the ascent cost, we can get this interplay between how expensive is it to spend time on the slope versus how expensive is it to just climb straight up the slope. And by using these two values together, we can produce some very interesting and natural looking results. So at this point, we wanted to sort of polish this so that it would be usable already inside of a game. What we might find ourselves doing is doing a subdivide operation to sort of create a slightly nicer looking path. And we may be to do a refine operation here, which is going to reset this to 0, set the second U to 1, and increase the tolerance to 0.5. We're going to see what happens is that the sort of the spline here becomes reduced down to a sort of a more manageable number of control points. And you can set that at the kind of cutoff point that you want to use. At this stage, we've already done 90% of the work. And the next thing we're going to look at is how we can expand the system so that we don't only support extending a single spline that we've added to the system, we also have the ability to draw out additional curves and have the pathing automatically react and update to those as well. So if you remember, inside of the vex wrangle, we just hard-coded the prim points to grab only the points from the first primitive 0. And we need to modify this wrangle slightly so that we accumulate all of the points for all of the primitives and add them to the lists, the string lists. So I'll bring up the geometry spreadsheet here while we're working so we can see those lists of attributes here. So we're looking to update the A and B with the paths of all of these primitives. We can grab all of the primitives on the geometry by using the code expand prim group, like so. And we're going to get the first input to the node, and we're just going to grab all the primitives. We could write in a group name here. So if you had multiple geometries coming into the input of this node, it would only look for the named group that you define there. And I'm going to call this group int prims. And much like before, when we were iterating over a set of points in the accumulate costs wrangle over here, this time we're going to do a for each, and we're going to look for a prim in the group prims, or the array prims. So we're iterating over every primitive that's inside of this geometry. Okay, so we're looking over all of the primitives, and what we want to do is we want to use the prim points function. So we know we're going to need this, and we want to get the current prim that's being iterated over, like so. So we're going to get the current prim, and we need to store this into an array. We can't use the points A array and the points B array here, because if we directly overwrite it, it's not going to be accumulating all of the points from each primitive. It's just going to be overwriting them with the points from each primitive. So we're never going to get an array containing all three primitives sets of points. So in order to accomplish what we want to accomplish, we need to initialize two new variables. And I'm going to call this new points A, and I'm going to call this new points B. Both are going to be arrays. And we're going to say new points A equals prim points, and we're going to do the same thing exactly as we did up here, except this time both arrays are grabbing the current primitive that's being iterated over. Then I'm going to cut the remove index code from below, and instead of updating the points A and the points B array like I was previously, we're going to do the same thing with new points A and new points B. Finally, I'm going to append to points A, new points A, and we're going to do the same. Points B, new points B. Okay. And the last thing we need to check is that we're not initially adding any points to those arrays like we were doing before. And we'll see that in the geometry spreadsheet now, we have this list of all of the point numbers across the whole geometry with the corresponding, so the index in this list will correspond with A, corresponds to the index of the point in list B, and that's what defines where the pathfinding needs to look when it's traveling from each point to the next point. And we can see now that indeed we have the ability to feed in multiple curves, like so. At this stage, you may begin to notice that it's slowing down a little bit, becoming a bit sluggish, especially if you add more paths and you're dealing with a high resolution terrain. So how do we avoid the slowdown from coming too extreme? Well, there's a few techniques that we can use. First of all, we want to remove this geometry, all of the geometry except the points. Why do we want to do that? Well, if we go and look at the find shortest path node and mouse over the adjacency array, we can see that when this is enabled, it's looking at the neighbors attribute on each point, and it actually creates a directed edge from each point to the points whose numbers are in the array. So that means it's not even using the, it doesn't even need to use the kind of skeletal mesh that we have here with all the triangles. It's going to construct an entirely new mesh. And we can prove this out if we use this add node and to delete all the geometry except the remaining points. And we'll see that we're just left with all the points, and yet find shortest path node behaves exactly the same. And we can see that this indeed is faster, because if we, I just pressed Alt-Y there to bring up the performance profiler. If we run the find shortest path node without the add node, it takes 0.56 seconds to run. And if we run it with that add node, it takes 0.356. So it's a little bit faster, and every little helps. So paths are covered, but what about rivers? Rivers are a kind of another kind of slightly more complex thing to consider, because unlike paths, rivers can only travel in one direction. And how are we going to go about supporting that? We already know that we have the ability to define different path costs in different directions. And we just need to modify this code so that we can distinguish between the cost of traveling up versus traveling down. So we need to add to this accumulate costs triangle a new variable called descent cost. If we go down into the loop, which is accumulating the values of traveling in each direction, we're going to essentially copy this exact line of code here and call it descent cost. Only we're going to add, make sure we spell it correctly, only we're going to add a condition. We're going to say if dot n and up, there we go, if this value of the sort of that describes how steep the slope is, if the value is greater than 0, that means it's positive, then we're going to start to accumulate the ascent cost. Okay, so we need to put this inside of this if block now. Additionally, if we're traveling up the slope, then we need to ensure that the descent cost is set to 0. Similarly, we need to do the same for the descent cost, except the inverse. So we're going to say, if the dot product of n and the up vector is less than 0, or less than or equal to 0, let's say less than 0, then we're going to set the descent cost to be this equation. Only we're going to create a new parameter called descent cost that allows us to control the weighting. Go. I'm going to set ascent cost to be equal to 0, because if we're traveling downhill, then there is no ascent cost. Finally, we're going to accumulate this cost along with the others, like so. And in theory, we now create the parameter that we've just created. We just promote that up here so we can modify it. We should in theory now have the ability to change the descent cost relative to the ascent cost. Only it's a little bit confusing. So we're going to create a new curve. I'm going to simplify things a little bit. I'm going to create a new curve. I'm just going to preview the terrain, and we're going to pick this point here, the top of the tallest mountain. I'm going to run it down to the sea. So I'm going to switch to an orthographic view. Yep, orthographic view, click right on the center of the mountain, and I'm going to click right on the border of the island like that. Okay, we'll wire that into the ray so we can be sure that our path is being projected to the correct location. There we go, that's our path that we've just drawn. And we can see that it starts on top of the mountain and ends at the bottom down here. And we're going to see how we get a difference in behavior if we modify the ascent cost relative to the descent cost. So if we get rid of all of the costs, right now the only thing being considered is the distance, and we just get a straight line towards the ocean. If we increase the ascent cost, put it quite high, we're going to see that the slope is going to, or the pathing is going to try to avoid traveling up the hill. So already we get a behavior that's looking slightly different. Okay. On the other hand, if we were to increase the descent cost, we're going to see that the path is going to avoid taking the steepest routes down the hill. And it's going to look a little bit more like the pathfinding algorithm we had earlier, where it takes the kind of more wiggly kind of route possible, where it stays on the shallowest possible angles, which looks quite nice. But for this pathfinding for a river, we definitely want to be using the ascent cost like so. So basically it's going to avoid traveling up any hills. So this is not bad, but we're finding that the path is sort of in some ways picking a peculiar options. For example, I would imagine that once the river sort of rolling down the stream arrives at this point here, it's more likely to want to continue to follow down in this path and down into this valley. But due to the way the pathfinding operation works, it's basically established it has to climb less overall hills to go this way. So this is too much of a simplification right now, and we're going to need to massage the channel of the river a little bit more deliberately too, so that it's encouraged to use these kind of recesses a little bit more. So we're going to introduce something new to the equation. If we go back to our source height field, we're going to use the height field mask by feature node to create a mask which is going to add some costs to the landscape. The cost that we want to add is going to be related to occlusion. We're going to modify the profile of the occlusion ramp ever so slightly so that I have a little bit more control over the costing. And we can see now that the red areas are going to be the areas that are expensive for the river to cut across, whereas the white areas are going to be the less expensive areas for the pathfinding to navigate. So we can see that these white areas, or the lighter areas in general, sort of identify sort of ridges and gullies that already exist in the terrain, which is perfect for a river that's going to be cutting through it. After we have created our height field geometry here, and we've sort of already optimized it down somewhat, we're going to use the volume attribute. So we're going to use volume rasterize attributes, or attribute from volume, sorry. So we're going to say points to apply attributes to, and we're going to plug the height field into the second input. And then we just need to pick the volume that we want to use, and the volume we want to use is going to be the mask. So now we can see that we have that occlusion mask being baked into this terrain. And when we can see it applied to the geometry like so, we may want to just go and tweak this further so that we can get a slightly different result. And I actually think this profile here, this round kind of fall off, is giving me the result that I want. So we're not going to call this attribute CD color. Actually, you know what? Let's leave it as that for the time being. Plug it in. You can see I've already also added a subdivide down here to increase the detail of the terrain. In fact, you know, what I may do is do the transfer after the subdivide to get slightly more high fidelity mask information. And then we're going to go down to the accumulate costs. I'm going to add one more cost, which is going to be a flat cost. Call this AO cost. AO, and this time we're actually just going to sample equals at CD. We're just going to grab the red channel of the color. They're all the same because it's just white at the moment. And we're going to multiply that by the AO cost, like so. Or let's call this, actually, yeah, this is maybe more appropriate to call this ridges cost. I'll call this ridges cost. So we look at the white areas, that's what they tend to be, the kind of rockier, ridgier, more exposed areas. And we can add that parameter ridges cost, leave it on 0 for the time being. And if we go down to the final accumulation here, the append, we can just go ahead and add the ridges cost as well. So now if we have a look at how that's influencing the pathfinding, it's not doing anything, and that's because we've set ridges cost to be not worth anything. If we just ramp this up, we can now see that we're getting a path that feels a lot more natural for the river. Only at the very end, it seems to take a path which is slightly less natural, and that's just because we have drawn this curve manually. So the very last thing that we need to do in order to complete this toolkit is to set it up to work properly with rivers. So instead of defining manual curves, which is a nice option to have, but it would be nice to have another option, which is instead of defining manual curves for rivers, we just define the kind of like the river source, and then we allow the pathfinding to do its thing. So the way that I'm going to do this, and I'm actually just going to color the river a nice blue as well, so we can clearly see that it's meant to be a river. So the last thing that we're going to do is we're going to customize the input geometry so that it's sort of easy for a pathfinding algorithm to find the way to the sea. It's going to always try and find the easiest way to the sea. And the easiest way that I've found to do that is to simply add a point, single point, which is at the origin somewhere. There it is. You can see if I move the camera, there's one single point that's been added there. Okay. And then we're going to add a primitive that connects from that point to every border point on this island. So I'm going to use labs border. I'm going to extract the borders, or not sort of extract the borders. I'm just going to use group, and I'm going to go group points. I'm going to call it edges or border or C, no, border. And then I'm going to say include by edges, unshared edges. It's going to take a minute to think, but it's going to grab all the border points. Then we're going to add that point there. In fact, we always want this, we want to know what the index of this point is. So I'm going to add it separately and then use a merge. That means this point is always going to be considered as 0.0 because it's being merged in first. And finally, I'm going to create a wrangle, which is going to say add prim of to geometry 0 of type polyline, and the points that it's going to use are 0.0 and the current point. And this little line of code here, as we can already see, is adding a line from, well, every point on the geometry to the center, which we don't want. And remember to just choose the borders. And now what we've got is an edge that runs from the border of our island right into the center. And why is this useful? Well, it's useful because it allows us to, from any source point on the terrain, target this point, 0.0, as the end destination, and the pathing is always going to path towards the closest point on the border that takes it towards that center point most quickly. So now we are going to plug this into the accumulate costs, like so. And we're going to, remove everything apart from those points. And then on the find shortest path algorithm, the last thing we need to do is provide an appropriate input, which is going to aim for this very last point. So we're going to grab that added point as well. And we're going to use, rather than using a curve input, we'll just do a quick scatter actually. So we're going to do a scatter onto the geometry, give us a bunch of points, but let's go with just 3 to begin with. Okay. And these 3 points are now going to target this point so much as we did before. We're going to do a quick little merge like so. And we're going to then, using a wrangle, for every point except 0, so I should have remembered to do this actually, every point except 0, I'm going to go over to here as well for, that's actually already working because it's grabbing the border. So for every point except 0, I'm going to add a prim from geometry 0 of to input 0 of polyline type polyline from the current primitive, from the current point num, sorry, to 0.0. Okay. And there we have created all of our primitives. And if we wire that into our create strings, we can have a quick little look, and we can see that indeed every point 1 goes to 0, 2 goes to 0, and 3 goes to 0. And that's going to give us the most appropriate rivers for any set of given start points. If I set this up to 15, 25, 35, or even 1,000, this can take a minute, we're going to end up with a beautiful kind of network of rivers that is always going to be trying to find the shortest and most natural looking route towards the sea. And if for whatever reason you're unhappy with the result and how it looks, you can go back to the accumulate costs function and you can give additional costs. Like for example, if I modify the ridges cost to a much higher number, let's see what the result gives us. And I like that more already. It feels more organic, a little bit more sort of weaves in and around these kind of ridges a little bit more. But it's not so, not a fan at all of what's going on over here. So yeah, you could play with these parameters to try and get the results to be more to your liking. But I think that that's enough for today's video. I'll be going deeper into pathfinding and inside of Houdini, and especially how you can build a set of tools that take advantage of Houdini and Unreal Engine, allowing you to build a nice kind of user experience around this basic functionality. And looking again inside of Unreal at how do we then, after creating these beautiful spline networks, have those be things that you can manually place and modify directly inside of Unreal. So I'll be going deep into the new scriptable tools framework inside of Unreal in future videos. So stay tuned for that.